Have you ever wondered how a computer plays a game like chess or even tic-tac-toe, not just well, but like perfectly? It really does feel like magic, but it's not. It all comes down to this incredibly simple but powerful idea about making the best possible decision when you've got an opponent who's trying to do the exact same thing to you. And it all starts with a game I bet you've played 1,000 times. So, to get our heads around this, let's just forget about supercomputers for a minute. We're going to start with a super simple game, one where it's actually possible to never, ever lose. Okay, so really think about it for a second. What does it actually mean to play a perfect game of tic-tac-toe? Well, it means that no matter what's on the board, you know the exact move that guarantees you either a win or, at the very least, a draw. But how do you figure that out? Okay, take a look at this board. It's O's turn, and X is just one move away from winning. The choice for O is totally obvious, right? You block. Of course you block. But why? Why is it so obvious? What's actually happening in your brain right now? You're not just thinking about your next move. You're thinking about what X is going to do after you move. And that is the absolute secret sauce. Your brain is playing out the future. It's going, okay, if I go here, they win. Nope, can't do that. But if I go here, I block them, and then they'll have to respond over there. See, this little back and forth, this anticipation, that's the foundation of all perfect strategy. All right, so let's take that gut feeling, that intuition, and make it official. How could we turn that very human thought process into a set of rules, a cold, hard algorithm that a machine could follow to play perfectly every single time? Well, it really just boils down to these 3 steps. First, you look at all your options. Simple enough. Second, and this part is the real game changer. For every single one of your potential moves, you have to assume your opponent is a genius. You assume they are going to make the absolute best, most crushing countermove possible. And then third, you just pick the move that leaves you in the best spot after you've factored in their brilliant counterattack. You know, it's kind of pessimistic when you think about it, but man, is it effective. You're not just hoping your opponent slips up. Nope, you're planning for them to be a grandmaster. For every move you could make, you ask yourself, okay, what's the absolute worst thing that can happen if I do this? And then you choose the move where that worst thing is actually the least bad. And this right here is the whole concept in a nutshell. You look at the potential for a maximum loss from any given move, and then you choose the move that minimizes that loss. Just let those 2 words sink in. Minimize, maximum. Because believe it or not, that's literally what this strategy is called. So it's time to put a name to the face and see exactly how a computer pulls this off so elegantly. And there it is, Minimax. You can think of it as the official rulebook for a brilliant pessimist. The entire strategy is built on one core assumption. Your opponent is just as smart as you are, and they will do everything they possibly can to make you lose. So how does a computer actually calculate all this? It doesn't just think ahead, it maps out the entire future of the game. It creates what's known as a game tree, this giant branching diagram of every possible move, followed by every possible countermove, and on and on and on until the game is over. Now, weirdly enough, the process starts at the very end. The algorithm looks at every single possible final outcome of the game, all the wins, losses, and draws. These are called the leaf nodes of the tree. And it just gives each of them a score. Super simple. A +1 if we win, a -1 if we lose, and a 0 for a draw. Okay, here's where the magic happens. The algorithm starts working its way backward from those endgame scores. When it gets to a point where it's your opponent's turn, we call them the minimizing player. Why? Because they're going to look at the moves available and choose the one that leads to the worst possible score for you, the lowest number, the -1. That minimum score is what gets passed up the tree. And then finally, we arrive back at the present moment. It's our turn. We're the maximizing player. We look at the moves available to us, and we see the scores that have been passed up, the best we can possibly hope for against a perfect opponent. So what do? We just pick the move that leads to the branch with the highest or maximum value. And that's it. That's the perfect move. That's Minimax. And listen, this isn't just for a tic-tac-toe. For a game like chess, the game tree is astronomically huge. It's hard to even wrap your head around. But this is the exact principle that allowed IBM's Deep Blue to defeat the world champion Garry Kasparov. It was looking dozens and dozens of moves ahead, calculating that Minimax value to find the perfect move against the best human player on the planet.
But what's really fascinating about Minimax is that its logic doesn't just live on a game board. This principle of preparing for the worst-case scenario, well, it shows up in all sorts of complex, real-world decisions. Now, I have to mention Minimax's close cousin, which is called Maximin. I know, they sound almost identical, but there's a really important difference. Minimax is for a true competition, a zero-sum game where if they win, you lose. Think chess. But Maximin is a broader strategy. It's about maximizing your own minimum outcome, even in situations that aren't purely about one person winning and one person losing. And once you start looking for this logic, you see it everywhere. It's the foundation of game-playing AI, of course. In economics, it's used to make huge business decisions when you have no idea what the market is going to do. And in politics, you could absolutely argue that the whole lesser of two evils voting strategy is a form of Minimax thinking. You're trying to choose the option that will do the least amount of maximum damage. You can even use this logic when there isn't an opponent at all. Sometimes you're playing what decision theorists call a game against nature, where your opponent is just the unknown. If you're deciding where to build a dam, you don't know for sure how bad the worst flood could be. So you use Minimax logic to plan for that absolute worst-case scenario to minimize the maximum potential damage. And this brings us to maybe its most profound application. We're going way beyond games and economics now. This is a principle that one of the most important philosophers of the 20th century used to ask how we should build a fair and just society. That philosopher was John Rawls, and he took the core logic of Maximin, maximizing the minimum outcome, and he applied it to one of the biggest questions there is. What does a just society actually look like? See, Rawls argued that a truly just society isn't the one that creates the most wealth for the people at the top. Not at all. It's a society that arranges itself to give the greatest possible benefit to its worst-off members. In other words, a just society follows a Maximin strategy. It works to maximize the minimum quality of life. It tries to make the worst-case scenario of being born into that society as good as it can possibly be. And that leaves all of us with a pretty fascinating question. From Tic-Tac-Toe all the way to social justice, this one powerful idea forces us to choose. In our own lives, in the big decisions we make, what's our play? Are we optimists, shooting for that best possible win, even if it means risking a huge loss? Or are we strategists, playing the Minimax game, carefully making sure that no matter what happens, we've minimized our maximum regret? It's a choice we all have to make.